Hi, my name is Taylor Wood. I go to Brigham Young University, and my project is the effects of surface treatment and anneal on polytriethylhexylthiophene infiltration in zinc oxide nanorod arrays. I've been working with hybrid inorganic-organic photovoltaics, which combine a zinc oxide nanorod array, which is the inorganic part, with an organic polymer. The polymer is the electron donor. The zinc oxide nanorod array would then be the electron acceptor. And the junction of those two will create an electron mobility charge current. The problem that we have with these is that the dissociation length of the exciton is about 10 nanometers, which is the reason why we have chosen zinc oxide to work with, because these zinc oxide nanorod arrays have a morphology of about 10 nanometers. And if we can intercalate the P3HT polymer into the zinc oxide nanorod array with 100% efficiency, then we can incredibly increase the charge carrier mobility and the photoelectric current of the solar cell device. So we began with fabricating our zinc oxide nanorod samples in an aqueous solution. We spin a sol gel seed layer of zinc oxide on and then put it in an aqueous solution of sodium hydroxide and zinc nitrate at 70 degrees C. A zinc oxide nanorod array will grow approximately normal to the substrate. And then we spin the P3HT polymer onto the top of that. So two things that we tried doing to increase the infiltration of the polymer were a thermal anneal and a surface treatment. First, with the thermal anneal, we annealed samples at 150 degrees C and 220 degrees C, and compared them against the sample that was unannealed. And then we rinsed off the surface layer of the P3HT so that we only looked at the data that was infiltrated into the nanorod array. What we found is that a higher temperature anneal will increase the infiltration of the polymer, but will decrease the ordering of the polymer, which is important because that increases the charge carrier mobility.
Any higher and it's shown.
So it also, we found that high temperature anneals blue shift a sample away from the solar spectrum, which is not ideal for a solar cell. So then we moved on to chemical surface treatments. We treated our samples with octadecane thiol, octadecyl triethoxysilane, and phenyl triethoxysilane. We found that the PTES, or the phenyl triethoxysilane, had little effect on the infiltration or the ordering of the polymer. However, the other two, the octadecane thiol and the octadecyl triethoxysilane, increased the ordering of the polymer, although it did not increase the amount of infiltration. So you can see in this area here. After that, we quantified our data and found a % infiltration. And what we found is that some of our samples showed % infiltration greater than 100%, which we attribute to a P3HT still on the surface of the nanorods rather than intercalated in. As you can see here, this SEM picture shows a P3HT sample before it's been rinsed and after it's been rinsed. And there are still areas of the sample after it's been rinsed that show P3HT. So in conclusion, we found that a thermal anneal, although it does increase the infiltration of the polymer into the nanorod array, it destroys the ordering of the polymer and blue shifts the sample. And that a chemical surface treatment will increase the ordering, although it does not necessarily increase the infiltration. So our future research is that we want to find some sort of happy medium between the two of those so that we can optimize the infiltration of the polymer and the local ordering.